Okay, and let's touch up this joint right here. A bit more solder. What? Did you see that, guys? Huh, I'll be darned. Usually need a power supply for this kind of circuit. Like, I'd expect the circuit to run in like 5-10 volts or something like that and draw around 20 milliamps at most, depending on how poor quality the LEDs are. So you'd expect it to need some 100 milliwatts, right? So where is it pulling the power from? Well, it's simple. It's pulling it from thin air. And as a segue to today's video, we're going to talk about power supplies. I currently have a Agilent, an Agilent, and a Keithley, and I've worked with a lot of power supplies over the years. And we're going to have a little chat about which power supply is the best for which application, and why the one I found on eBay recently is the best one I've ever seen. So let's get into it. Okay, so here are the two power supplies I currently own. Because I lied, the Keithley isn't a power supply, it's a source meter. But we'll get into that. So let me turn on this one so you can hear why I don't like to keep it turned on all the time. So the transformer in this unit, which is 40 watts, and the fan, the transformer is bigger than in the Agilent. So it's only, it's got two channels, a 15 volt 3 amp channel and a 12 volt 1 amp channel. So 40-ish watts, 50-ish watts, something like that. This transformer goes up to here in the power supply. It spans almost the entire width of the instrument, and it's almost up to here. It's massive. I'll show you the insides a bit later. The Agilent I got new, and it costs around 600 euros or something like that from We Electron. I didn't get any discount codes because reasons. But anyway, it actually went back to service because there was a issue with the main board. There was a power supply rail being dragged down, and when you turned on the parallel or series connection relays inside, it would reset itself after a few minutes. The LCD would do weird flickery effects and it would just reset itself. So why do I like this power supply so much? Well, I don't like it because it's loud. I don't like it because it's heavy. It's very big. It's deeper than the Agilent and heavier. But it's excellent in two respects. So first of all, it's got a very nice, basically 4.5 digit resolution for current, and 3.5 or 4.5 digit resolution for voltage on both channels. But on the main channel, channel 1, it actually goes up to 1 microamp in resolution. So it has two ranges. This range stops out at 20 milliamps, but it has a 1 microampere resolution, and the other one, which is the interface is very, very, very hard to use. The other range goes up to 100 microampere resolution, but up to 3 point something amps. So the maximum is around 3.2 amps. So it's got very, very good current resolution when you're measuring for example, sleep current of various devices, like embedded devices and stuff like that. It also has an excellent piece of software that you could buy from Keysight. You can't really, I haven't seen an offer for how much it costs or anything, but I got the trial. So the software allows you to connect to the power supply and do various plots and actually use it like basically a small 60 kilohertz oscilloscope for current and voltage. So you can measure the current being drawn, and it can trigger off of different current waveforms, and I'm going to show you all that in just a second. But the most interesting thing to me for this power supply is that excellent current resolution, and that it's a very, very high quality power supply. So it's built like a tank. It's got a massive transformer. It's got a load dependent fan, but you're going to see that it's quite loud. So even when it's not drawing any current, it's quite loud. Another disadvantage of this kind of power supply, because it's a system power supply, it's a mobile communications DC source, so it's not a lab power supply theoretically, is that it's meant to hang around in the back of a rack in a giant piece of industrial equipment on the assembly line or something like that, or on a long-term test bed or something like that. So it has no banana binding posts. Though, if you look inside, there's two cutouts, giant cutouts in the plastic of the front casing, which would allow you to mount some binding posts in there. I'm not sure if this is a reused front chassis from any other number of instruments that Agilent used to make back in the day, or actually HP. But this one never had banana jacks. Other models from other lines in the same form factor might have. And I assume that there are some one unit, like actually half unit power supplies from Agilent or Keysight nowadays, which fit in this form factor, have the knob, have this interface on the front, and have two binding posts. So they might have reused this plastic chassis for something else. Mind you, just the front is plastic, the rest of the instrument is very thick steel. The Siglant is very nice as well, so somebody did a video about the Siglant a while back. It's a very good power supply, it's very clean, it's very not noisy, neither electrically nor audibly noisy. But it still left a bit of a bitter taste for me, because it actually died, and it died when I kind of needed it pretty bad, and I had to wait for it to get back to Germany, where Sigland took it apart, repaired it, and sent it back. It didn't take too long, but it was unpleasant nevertheless. So this is just my experience. I haven't seen many other failures on this model of power supply, but it's something to beware. Anything can fail, and this being a Chinese product, quality checks on them, I wouldn't expect them to be as good as on something like a Keysight or a Keithley or a, I don't know, Rohde & Schwarz power supply. But come on, those Rohde & Schwarz power supplies were made by Hameg in the past, and they just put another user interface on them. So I don't know. It's mixed bag. You do you. This is not a review. It's just an explanation for why I think this is one of the best power supplies you could get on the used market right now. Okay, so for now I have it set to 3.3 volts. This is the default state in which it boots. You can change that in the configuration menu in the application, the software that runs. And I'll start that software up, and we can talk about it and why I find this power supply so interesting. Okay, so let's do that. Okay, so you can see that the software is a trial and it only goes for 15 days. So yeah, I'm sad that I'll have to say stop to quit using this software, but it runs on GPIB, and I could probably figure out a way to use Pi Visa or something similar to do what this GUI is doing. But it's honestly kind of nice as it is already set up, and reverse engineering it, or actually doing it from scratch, would be kind of a bit of a pain. So I'm going to click OK, and here I'm going to connect this. This is a remote control from a video camera that I got at a flea market a while ago. So this is the negative terminal, and this is the positive. And you can see that it's not even drawing 100 microamps basically. So if we go to on this software, if we go to the current range measurement and look at the display, there's basically not even a microamp. Okay, but if we go to trigger and set the trigger at a positive slope, go to a different range, because you're gonna see why, and set the trigger to around 100, and 2 milliseconds per division is fine, and we're gonna go to 20 milliamps per division, and we hit measure. It's saying that it's waiting for a trigger, and I'm gonna give it a trigger. All right, I'm gonna push this button. Oops. And what we have here is apparently not at the correct range, and I'm gonna hit auto scale. So what you can see here is the current draw of the remote control from the power supply, while it's sending a burst of basically LED flashes. It's flashing this infrared LED it's got at the front. I am actually shorting things out, doesn't matter. So it's got this infrared LED, and something that you might have not known is that they drive the hell out of those LEDs in order to get any useful range whatsoever out of them, and to enable them to work in like lit areas. So this usually was powered from a 2032 coin cell, and it would have never gotten this amount of current from the coin cell itself, but it has a giant tantalum capacitor on the board, which was actually meant to serve as a an accumulator, like a big bucket that could charge up and then discharge into a massive pulse of flashing light in this LED, right? So still, even this requires quite a lot of current from the input side, and I'm not sure actually if you'd simulate the internal resistance of a CR2032, if the peaks would go up as high as they did here. This is a thing I've observed in the past when I used to work in medical devices. So we had an implant about the same size, but on a flex PCB. I would show it to you, but I'm not sure that would be great for me. Anyway, the thing was basically it had 4 channels of source and measure instruments inside, so it could source an AC current or a DC current and could measure them as well. Sorry. And when it did that, it had some boost converters which would take the power from the battery, which was a single cell lithium iron thionyl chloride or something, one of those implantable batteries with very low self-discharge rates and very long shelf lives. But the disadvantage of those cells is that their internal resistance is very, very large. So it would take power from the battery to generate plus minus 15 volts. And in doing so, you could observe that the battery voltage would drop significantly, like hundreds of millivolts. And in their good day, those batteries had like half an ohm of internal resistance. When they were almost dead, their internal resistance was over 2 ohms. So you can imagine that trying to draw any significant amount of current would basically mean that the battery would flatten, like completely drop all its voltage. So when I was measuring the current consumption of one of those things, I used to use the microcurrent, right? Which has a reasonably low burden voltage shunt resistance. So compared to what was previously used to measure the current through that device, which was a plain 1 ohm resistor in series with the supply, which they connected to the oscilloscope to use as a improvised shunt, the 10 milliohm shunt resistor from the microcurrent was much, much smaller. So they could see that instead of drawing a peak of a couple of hundred milliamps from the battery, the device would actually be able to draw up to an amp in short bursts. So basically, that was a discovery that meant some things had to be reconsidered. So yeah, this is an extreme case, so basically zero power draw in standby, but the massive amount of power draw when it's actually doing something, because what it needs to do is yell out in infrared at a TV, I'm here, change to channel something, or actually to a camera, and it has to yell something like zoom out or zoom in. So it needs to be able to do that from quite a ways away, and it needs to do that very reliably. So that poor LED, the small LED here you're seeing, is actually being driven to hell and back. Okay, let's try a different device, and for this I'm gonna bring back the thing from the last flea market finds, and we shall look at this device. Okay, this is the Geiger probe I found, and I figured out the pinout and reconnected the Fisher connector to it, and actually resoldered the cable to the connector, and it's working fine. But if we go into the software here, we should go to actually the small current range, and I'm gonna set it on auto trigger, and I'm gonna leave it do its thing and see if we can find what I was looking for, which is that this the converter, the high voltage converter inside, has actually not doesn't actually draw current continuously. It's actually got a pulsing behavior of some sorts. As you can actually sort of see on the screen, so it goes from 20 something microamps to pulses of 300-400 microamps. So I'm trying to get it to do something. Yeah, okay. So as you can see here, the peaks are basically up to the high range of the power supply. They're almost exceeding the 20 milliamp that you would that you would have on this power supply's range. So as I said, low range is 20 milliamps with a 1 microamp resolution. High range is the full power of the power supply, but with a 100 microamp resolution. Okay, so you can see that the pulses this converter inside is drawing are about, let's put some markers here, and we can put one here and the other one here, and let's see, they're about, delta is around about a millisecond long. They are up to around a maximum of 18 milliamps. So for this part, the converter inside, what I assume is doing is drawing, and it's not correlated to the impulses on the Geiger tube. I've checked this. So what it's doing is basically it's firing up for a few milliseconds, and then it's charging the capacitor that stores the high voltage for the tube, and it's waiting for it to discharge before it turns on again. So it's not a continuous mode. Basically it's running not running constantly in order to save battery life. And as long as the Geiger tube hasn't got anything to measure and it's only measuring background radiation, the current draw should be very small. But I have this Iranian glass in form of a shot glass and some beads. A good friend of mine sent them to me. And let's see if we can see any difference in the behavior of oh, it usually says not responding because, you know, older software. So apparently this radiation source I have here isn't strong enough to make the converter run more often and for longer periods of time. So this is another case where you would use a power supply like this in order to figure out the behavior of a device. Because if I plug this into the Siglant will not show me anything. Yeah, so speed of reading 60 something kilohertz at the high end for this power supply. Resolution, microamps. It's got a few disadvantages, and I'll talk to you about them a bit later. But I think it's time we take a look inside and see what makes it tick. Okay, so let me set things up and I'll get to you in a bit. Okay, so this is the insides of the power supply. It's so big that I can't fit it in the frame all at once. Moreover, I'm sitting up, so if you see me like jerk the table, I'm sorry. So as I said, big transformer, very big. Filter capacitors. That seems to be a synchronous rectifier, or just a rectifier made out of diodes in TO220 packages, which is crazy. Some voltage regulators for the various analog voltages inside. This might be a 7805 with a heatsink, properly screwed down. None of the rubbish you've seen so far in like Dave's video on the Regal power supply, where there was one of these hanging around at 100 something degrees seam, right? And this is a logic board, and I'm going to remove some screws on this side which hold the board in through the means of the GPIB connector and this serial connector. So these are the only things holding this board in place. So give me a minute to do that and I'll be right back. So as you can see, inside we have some bodges, which is not uncommon. Funniest thing that I find around here is that this is the main power input, and this is all precision analog circuitry. These are precision resistors and a few bodges. It's probably using some sort of synchronizing with the power lines to improve on the noise of the power supply, basically the readings, as any other multimeter would do. A multimeter is usually synchronized to the power supply, to the mains frequency, in order to get to make sure that each reading has the same amount of power line noise, or that the noise is being cancelled out. So yeah, loads of analog components on here. You can even see guard traces, the shiny silver ones are here. I don't know what this capacitor is doing, but I'm assuming it has something to do with when the ranges switch. It ensures that there's no glitches in the output voltage. And on this board, there is an incredible amount of logic. So Xilinx Spartan 3 FPGA, or actually not, I think it's a Spartan 3. Texas Instruments DSP 32 320C32. This, I think, is the main application processor, probably ROM and GPIB interface or some description. Basically, this entire bit should be something along those lines, because this is the GPIB interface. And it also has some relay drivers around here. So it has a connector, like one of those Phoenix connectors, which connects to relays or external inputs or outputs in something like a an industrial application where you need to signalize that a power supply is a device under test has passed, or something of those sorts. This is an AD677. I think that's the main ADC for the whole device. Yeah, so that's a 16-bit, 100 kilosample per second, 1 LSB integral non-linearity. So this is a pretty good ADC. It's actually almost 4.5-digit multimeter class or something like that. And yeah, this is basically taking the readings for the current, and we got a load of supporting circuitry for it. Um, and yeah, a lot of basically all of the processing for the entire power supply, the readout for the current and the setting is done by these two devices right here. So I'm gonna put this back together, and I'm gonna show you the last thing I wanted to show you in this video, because it's kind of dragging on again and I don't know how to keep videos short. So my last point here was why you should consider, first of all, getting used equipment rather than new equipment if you want to start a hobby in electronics. And why, if I were you, I would get not necessarily a Keithley, but why I would get something like a source meter, or like that Agilent I showed you a few minutes earlier. Why I would get something like that as a power supply. First of all, why I would get something used and broken. Well, first of all, if you get something broken, you have to fix it. And how do you get to fix something like this source meter? This one actually worked fine from the beginning, but others may not be so lucky. You take the user manual, the schematics, Keithley made them public, and you dig inside them and see what's wrong. First rule of troubleshooting is thou shalt measure voltages. You measure voltages, and then you start to understand how this thing was built and how it was constructed and how the designers intended to do the things that they did. Now, if you start to understand, even if you can't fix the thing, then it's still a learning experience. And I know it's kind of expensive as a learning experience, and usually you'd be better off fixing things. And I'm not making a great case for myself here, but usually the things that break in these things aren't as important as like the unobtainium Koto relays in here or stuff like that. Usually what breaks is a tantalum capacitor gets shorted, or an electrolytic gets blown up, or a 7805 dies, or the worst one I found was in my electrometer, and if you want I'll do a video about that. In my 617, the main integrator basically died. So basically the ADC of the thing died, and it was just showing 0 all the time. So usually that's what these things fail. Now oscilloscopes, that's a different story altogether. If this is dead, then this is not fixable. This has probably died because of an ADC is dead, and these have hybrids. Like the front end is a hybrid filled with attenuators, and this is screaming at me that its attenuators have gone over their useful lifetime and they need to be replaced. So when this thing is gone, it's gone. It's not even a computer that plays Doom anymore. It's a brick weight. It's worthless. But this thing can be fixed. So most of the Keithley things that I've come across in the recent past year or so, since I've started accruing them, I've been able to fix or understand their working principle quite easily. So that's one of the arguments why you should get something used, like a broken piece of test equipment. The second reason is we have to stop filling up the landfills. We have to stop making cheap consumer electronics like this piece of crap multimeter, which costs like 20 bucks but is a piece of crap, and I only bought it to give to a student because I couldn't like give him a fluke or something like that. But we have to stop consuming so much product. We have to stop making things again when they're already around, and resources are scarce and precious, and we need to conserve them as much as possible. And the last point that I was going to make about getting used stuff, this thing was the Rolls-Royce when it was launched. It was in excess of $10,000. These things were incredibly overly engineered. They were designed to be as good as possible, to get the highest performance that it could get. in the current ranges, this thing is still as good as the brand new 2450 series. Like, it's still got the same resolution, still 10 femtoamps in the measurement resolution, right? Only the brand new electrometers from Keithley do any better than that. And those barely do better than the 30-year-old shoeboxes. So they already were at peak technology back then. So there's no reason to invest in something brand spanking new, which costs $5,000 or $6,000, even if you have that amount of money. And for hobbyists, that's very hard to justify. But for $300 or something like that, especially if you're in the States, this is unbeatable. It's also kind of about the best power supply you can get in terms of noise, both current and voltage noise. These are very, very good. And the compliance, which means basically the current limiting or the voltage limiting when it runs as a current source, is on par. Like, there's nothing as good as it. First of all, if you set like 10 milliamps here or 100 microamps or something like that, or a nanoamp, it will never go over that nanoamp. It will never overshoot. It will never. Some devices might latch up because of that current, that compliance limit being so good. So I had a problem with that Geiger counter probe. I set it to a reasonable 20 milliamps as a current limit, and like this, and it would just turn on and go into compliance, which means that this thing is current limiting, and it wouldn't work. And I cranked up the current limit to the full 110 milliamps, actually, for 100 milliamps, and it worked, and it drew less than a microamp. But that's what goes to show this current limit is so good, and it acts so fast, that it drove the logic devices, or whatever the hell was going on in there, into latching up. So the devices latched up, they are shorting out, and yeah. So bottom line, you learn a lot by fixing things. You save the environment, because this thing doesn't go into the landfill. You don't waste resources on making the high precision op amps and the electrometer op amp inside here, or the Zener diodes, or whatever, the carbon film resistors and the capacitors, and you might have to replace the capacitors, but anyway, it's better to replace a few capacitors in a thing like this than to buy a whole new power supply that had to be manufactured as cheaply as possible today. Imagine the amount of cost that went to, and resources that went into the assembly line for those things. These were made in the thousands of units, I assume tens of thousands at most. So these were mostly man-made, manufactured by hand. I don't think anybody made the dedicated assembly line for a 236 or a 237, right? So get used, save some resources, learn yourself a thing or two about electronics, and yeah, that's about it. That's how Jim Williams learned electronics, I'm pretty sure. I might be talking out of my ass here. He, of course, knew all the mathematics behind it and everything, but to my mind, there are some things that you can't just learn from a book, not even from The Art of Electronics. And those things you only learn by doing things. Practice makes perfect, as they say. I have sidetracked so many times that Grandpa Simpson has nothing on me. So, in short, look for used pieces of test equipment, fix them, learn electronics, and if you want to, that's up to you. And if not, look at me trying to fix things and showing you the things I have fixed or the things that I've accrued, and maybe we can even get to do some projects at some point in the future. Thanks for watching. Bye bye.